You ever wonder why your phone buzzes, or why your car has that little rumble when you're at a stoplight? Well, it all comes down to one of the most powerful, and sometimes one of the most destructive forces in engineering: vibration. So let's dive into this hidden world of shakes, rattles, and oscillations.
Okay, I know it sounds like the beginning of a weird joke, but the answer is actually the exact same underlying physics. That annoying thump, thump, thump from your washing machine when the laundry's unbalanced, it comes from the same place as the catastrophic failure of a massive structure. Both are just unwanted vibrations getting totally out of control.
So what are we really talking about here? At its core, vibration is just a simple back-and-forth movement around a central point. Think of a guitar string right after you pluck it, or a kid on a swing. It's this really fundamental motion that is, believe it or not, all around us, in pretty much everything that moves. But here's the thing. Vibration isn't always the bad guy. We actually rely on it to create music with instruments and loudspeakers. In most machines, though, it's a huge problem. It wastes energy, it creates a ton of noise, and more often than not, it's a giant red flag that something is about to go wrong. Okay, so if these vibrations are causing our machines to wear out and break down, where are they even coming from? Well, engineers kind of have to play detective, and they have a list of the most common culprits, the usual suspects, that they check first when everything starts to shake.
And here they are, the 6 most wanted offenders in the world of mechanical vibration. Things like unbalance, misalignment, and just plain old loose parts, they're responsible for the vast majority of problems. But you see that last one on the list? Resonance? Oh yeah, that one is in a league of its own. Let's start with the most common one, unbalance. Imagine you get a new tire put on your car, but the mechanic forgets to balance it. You get on the highway, and as you speed up, the whole car starts to shake, right? That's because there's a little heavy spot on the tire that's creating this force pulling it off center with every single rotation. The exact same thing happens in big industrial machinery, just on a much, much bigger scale.
And now for the big one, the phenomenon that can take a tiny, almost harmless vibration and amplify it into a force that can literally destroy a structure. This is where we get into the really high-stakes, mind-blowing physics of resonance.
So to really get resonance, you first have to understand this concept called natural frequency. Every single object, everything, from a wine glass to a skyscraper, has a specific frequency that it wants to vibrate at if you disturb it. If you tap a tuning fork, it will always, always ring at the exact same musical pitch. Well, that pitch is its natural frequency. So here's the crucial part. What happens when an outside force, say the wind or the hum of an engine, starts pushing on that object at its exact natural frequency? Well, the energy starts to add up with each little push. The vibrations get bigger and bigger and bigger until the whole system can just completely fail.
And this right here is the ultimate cautionary tale, the infamous collapse of the Tacoma Narrows Bridge back in 1940. A steady wind, nothing crazy, just a steady wind, happened to perfectly match the bridge's natural twisting frequency. The bridge started to sway a little. Then it started to oscillate violently, with more and more amplitude, until the structure literally tore itself apart. It's a powerful lesson for every single engineer.
Okay, so we know what causes vibration and just how dangerous it can be. So how do we stop it? Well, fortunately, engineers have developed a whole toolkit of really clever strategies to fight back against these unwanted forces.
These are the 5 fundamental approaches. Each one tackles the problem from a totally different angle, from fixing the source directly to cleverly making that vibrational energy just disappear before it can do any damage.
The most straightforward solution is always just to go after the source. If a machine is shaking because a part is unbalanced, you balance it. If parts are misaligned, you align them. It's like preventative medicine. You fix the root cause so the vibration never even becomes a problem in the first place. This next one is actually kind of beautiful in its simplicity. It all goes back to Newton's second law. You remember, force equals mass times acceleration? So if you have a constant force that's causing the vibration, you can reduce the actual shaking, the acceleration part, just by increasing the mass. Yeah, sometimes the best solution really is to just bolt the machine down to a heavier block of concrete.
Now these two often go hand in hand. Tuning just means changing the structure's stiffness or its mass to shift its natural frequency away from any external forces so you can avoid that whole resonance disaster. Isolation is even simpler. You basically just put something squishy, like a rubber mount or a spring, between the vibrating machine and whatever it's sitting on to stop the shake from spreading.
Damping is, in my opinion, maybe the most elegant solution. Instead of just blocking the vibration, it actively gets rid of it. A damper, like the shock absorber in your car, uses a fluid,
usually oil, to convert the energy of that vibration into a tiny, tiny amount of heat. It effectively just kills the oscillation.
So that's the classic toolkit. But today, the fight against vibration has gone seriously high-tech. We're moving from simple mechanics to smart systems and powerful computer simulations that are completely changing how we design, well, everything.
A really key evolution here is the shift from passive to active damping. Okay, so passive systems are your classic shock absorbers. They just react to whatever happens. But active systems, they're smart. They use sensors to actually detect an incoming vibration, and then they use actuators to generate an equal and opposite force to cancel it out, all in real time.
But you know what's even better than canceling vibrations? Designing them out from the very start. With today's software, engineers can build a perfect digital twin of a machine or a building on a computer. They can simulate any force you can think of, wind, earthquakes, engine cycles, and see exactly how it will vibrate, letting them fix problems long before a single physical part is ever manufactured.
So what does this look like at the most extreme scale imaginable? I'm going to leave you with one number for a second. 660 tons. What on earth could possibly need a 660-ton solution for a vibration problem?
The answer? One of the tallest buildings in the world. The Taipei 101 skyscraper has a massive 660-ton steel sphere suspended near its top. It's a giant pendulum called a tuned mass damper. So when high winds or even earthquakes start to push the building one way, this giant pendulum sways in the opposite direction, canceling out the motion and keeping the whole tower stable. It's vibration control on an absolutely epic scale.
So, from the tiny buzz in your pocket to the colossal dampers that protect skyscrapers, controlling vibration is this constant, invisible battle being fought by engineers every single day. The next time you're on a smooth car ride or working in a quiet, stable building, maybe take a moment to wonder what other invisible engineering is out there, just keeping our world from shaking itself apart.